Welcome everybody. I hope you guys are doing well. Today what we're going to do is we're going to have our first virtual class. We're going to pick up by reviewing electron configurations. All right, on the board, as you can see, I have the periodic table method of doing a electron configuration. What I'm going to ask you to do is have a periodic table handy so that you can see the elements and the atomic numbers as I go over this. We'll start with a review first, and then there's a couple of new things that I'm going to show you. First, using the periodic table method, we can come up with the master sequence, which we're going to review that in just a second. Today's objective is going to be to write electron configurations, orbital notations, or orbital diagrams. This is the one with the boxes and the arrows. How to determine what block the element belongs to, how many unpaired electrons there are, and something new is a shortcut. It's known as the noble gas configuration. I'm going to put here shortcut because it's an abbreviated configuration. So let's go ahead and get started with the master sequence. The master sequence would be if our building was full of electrons. That honor belongs to oganesson, which is the largest element in the periodic table, number 118. And using the periodic table, and you can follow along up here, as you go across, the first one's 1s2. Then you go to 2s2, followed by 2p6. Then it's 3s2, 3p6 right here. Now, look at this, how it changes. It goes to 4s2, and then it's 3d10. Not 4d, but 3d. It's one number lower. So this is 3d10, followed by 4p6. Go to the next row. 5s2, followed by 4d10, followed by 5p6. Now, the last two rows, we have to incorporate the lanthanide and actinide series. So when you start off, it's 6s2, but then you got to remember the lanthanide series belongs in that box. So after 6s2, you'll notice it'll be 4f14. Then you go back here and complete the row. 5d10, followed by 6p6. And our final row is 7s2. Again, the actinide series belongs here, so it'll be 7s2. Then you go to 5f14, then you go to 6d10, and I know here this is an older periodic table. This should be green, and that would be 7p6, and that would take you to the final one, which is oganesson, which is the one you see on the board. Okay? So what I wanted to do is I wanted to pick an element, and I wanted to answer these questions using the elements. So what I'm going to do first is, let's pick an element. I'm going to go ahead and choose something medium size. I guess nickel, okay, the element nickel, Ni. Okay, on the periodic table, he's number 28. That means he has 28 electrons. So the first thing we're going to do is, using the sequence, let's do the electron configuration for nickel. So you start off with 1s2, then you go 2s2, 2p6, 3s2, 3p6, 4s2. Now, so far, if you count the superscripts, that's 10, 20. Our next guy is 3d10. Well, now, D can hold up to 10, but we've already put 20. We only got 6 left, or I'm sorry, 8 left to get us to 28. So what we're going to do is we're going to put here 3d8, because we don't have 10, we have a maximum of 28. The way you check is if you add the superscripts, they're supposed to add up to the number of the atomic number. So that's the electron configuration for nickel. Now, one of the things that before I get into orbital notations is this is color-coded. Okay, the periodic table is divided into 4 blocks. All right, the S block is the first 2 columns. There's an exception. Helium belongs to the S block. So the S block is the alkali metals and the alkaline earth metals, and also it includes hydrogen and helium. The P block is groups 13 through 18. It's this green spot over here. They all end in the orbital P. The D block is groups 3 through 12. These are the transition metals. And then down here where you got the lanthanide and actinide series, these two rows down here form the F block. So the way you determine what block an element is in is when you do an electron configuration, you look at the last one. This ends in a d orbital. That means that this element is in the D block, and you'll notice nickel is actually over here. In fact, if you look, that row is called the 3D row. This tells you the period, okay? So he's actually over here. This is D1, D2, D3, D4, D5, D6, D7, D8, and you will find that nickel is in D right there, okay? Now, don't forget the maximums. S can hold up to 2, P can hold up to 6, D can hold up to 10, and F can hold up to 14. So this element belongs to the D block, okay? Now, here's what we're going to do. We're going to do an orbital notation. The difference is we're not going to use superscripts. We are going to use arrows to represent the electrons. And we're going to draw boxes. The boxes are going to represent the rooms or the orbitals. Now, what you need to remember is how many boxes to draw. And I think you guys know this already. An s orbital has only one orientation, so every time there's an s, we'll draw one box. The p has 3 orientations, so you'll draw 3 boxes. The d has 5 orientations, so you'll draw 5. And the f has 7 orientations. So let me show you what I mean by this. So you're going to draw 7 boxes for that. Use this as a template. Since that's an S, you're going to put one S, and then you're going to draw a box. Don't put a little 2 here. Instead of putting the superscript, we're going to put 2 arrows. Now, one arrow has to go up and one down, and this is important. The arrows pointing up and down implies that the electrons are spinning in opposite directions. If you recall, the spin quantum number says that they must have opposite spins in order for them to get along. So show one arrow going up and one down. Do not put them both up or both down. That would be incorrect. Let's go to the next, let's follow to the next one. 2s. Again, it's an S, so it's one box, up, down. Now we finally get to a 2p orbital. When you get to a p orbital, draw 3 boxes. And then we're going to incorporate something called Hund's rule. Look what Hund's rule says. I need to put 6 people. This is the correct way. When you use Hund's rule, you first put the first person in the first room, then the second person in the next room, the third in the next room. Now every person has a room now. I got 3 more people because there's 6. Once you put 1 in each room, you go back and you pair them off. 4, 5, 6. This is the correct way to assign the electrons. So you go 1, 2, 3, go back, and then you go 4, 5, 6. Do not go 1, 2, 3, 4, 5, 6. You violate Hund's rule. Then we go back to an S, so you're going to put 1, 2. Okay, that one's pretty easy. Back to another P, so you're going to draw 3 boxes. Here's Hund's rule once again. 1, 2, 3, 4, 5, 6. Due to space, I'm going to go down here. The 4s, again, it's an S, so it's 1, 2. And then finally, when you get to the d orbital, you're going to need to draw 5 boxes. 1, 2, 1, 2, 3, 4, 5. Now, look at why Hund's rule is important. Here's where it really matters. There's 8. So you go 1, 2, 3, 4, 5, then go back. 6, 7, 8. That is the difference between an electron configuration that's an orbital notation or orbital diagram. Notice there's a question that says, how many unpaired electrons are there? Well, all you got to do is look at the last one, because everybody else is paired, and you'll notice there's 2 electrons that are unpaired. So the answer to this question is 2 that are unpaired. Okay? If everybody was paired, you'd put 0. All right? If a room is empty, you don't count that. It's just empty. So when I ask you how many are unpaired, just look at how many arrows are by themselves, and that'll be the answer. Now there's also a shortcut to this. It becomes very practical as the elements get much larger. So what you're going to do for the shortcut, notice that nickel is in period 4. Nickel's right here, okay? What you're going to do, and if you follow along with me on the periodic table that you have, it's called the noble gas configuration because we're going to use one of the noble gases as part of the shortcut. You see, nickel is in period 4, so if you go all the way down here where the noble gases are, you'll notice that in period 4, krypton is the noble gas of period 4. But you're not going to use krypton. Here's the rule. When you're doing the shortcut, you're going to use a noble gas, but you're not going to use the noble gas of where you're at. You're going to use the noble gas of the period above where you are. So nickel's in period 4. You're not going to use krypton, which is on period 4. You're going to use the noble gas from period 3. That honor belongs to argon. Argon is the noble gas in period 3. Now, argon, if you look at the periodic table, has an atomic number of 18. If I asked you guys right now to draw argon, it would look like that. Because that's 10, 16, 17, 18. That right there, you're looking at the electron configuration of argon. I'm going to draw a little line here for a minute. That's the electron configuration for argon. Okay? So here's what you do for the shortcut. Find out where you're at. We're on period 4. Go to the noble gases. Don't pick the noble gas of the same period. Look at the one above, in this case argon. Argon's configuration is all of that. Instead of having to write all of that, and this is why it's a shortcut, what you do is replace or substitute this with a symbol for argon, put it in a bracket. That represents from here to here, but you got something left because it's not argon. We have nickel on the board. So after you put the bracket with argon, then you put what's left. And that's the shortcut for nickel. He represents the first 18 electrons. That's 19, 20, 28. This is the shortcut or the noble gas configuration for nickel. Okay? So I wanted to show you guys that. We'll do another one now, but this is the one new thing that we have not covered. Okay? So let's go back. I'm going to pick another element. Let me pick something a little different here. Let's pick something like, all right, let's go with antimony. We don't usually see that one. So I'm going to erase this, and what we're going to do is we're going to do the same 4 questions for antimony. Antimony, the symbol is SB, okay? And the number is 51. 51 electrons, okay? So let's start off by doing an electron configuration. So we're going to stop at 51. So you go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10. Let's see where we're at. We got 10, 20, 30, 36, 37, 38, 48. Oh, we're close. Here we go. 48. The next one's 5p. So 49, 50, 51. We are going, this can hold 6, but we got 3 left. That adds up to 53, or to 51. So that's 48 plus 3. Now notice, it says 5p3. If you look at your periodic table, you'll see that over here, here's 5. This is P1, P2, P3. You're going to see that antimony is right there. Okay? This is P1, P2, P3. He's 5p3. Okay? So that's the electron configuration. Now, let's do the shortcut since I just taught you that. Since antimony is in period 5, if you look at period 5, the noble gas of period 5 is xenon. But we're not going to use xenon. We're going to use the noble gas of period 4. You're on period 5, you use the noble gas of the period above. Krypton is the noble gas of period 4. That's the one we're going to use. If you look at your periodic table, krypton is number 36. So that's 10, 20, 36. I'm going to put a line there just so you know. This is the electron configuration for krypton. So what I'm going to do is I'm going to put it down here in a bracket. Okay? That represents the first 36 elements, and then you write what's left. And that would be the shortcut. 36, 38, 48, 49, 50, 51. That's the shortcut. You just use the noble gas part of the period above where you're at, and that's how you do the shortcut. Okay? Now, let's answer the rest of the questions. You could tell he's in the P block. Okay? So this one, let me erase this from the previous question. He belongs to the P block. And this one's going to be a little bit tedious, but let's do the orbital notation for antimony. So you put 1s, every time it's an S, one box, followed by 2s. Then we have a p orbital, so make 3 boxes. Don't forget to use Hund's rule. Okay, then you got back to 3s, that's 1 box. Every time you write a p orbital, make sure you do 3 boxes. 1, 2, 3, 4, 5, 6. That's Hund's rule. Again, we go back to a 4s. Okay. Then we have a 3d here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I'll go back over here. Let's go to 4p. 1, 2, 3, 4, 5, 6. Back to a 5s. Then we got a 4d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice I'm using Hund's rule. And then, this is why Hund's rule is very important, because each person has their own room. That's the orbital notation for antimony. Now we can also use the last one to answer how many unpaired electrons. You can see here clearly there's 3 unpaired electrons. Okay? So the only thing new really that I've shown you is the noble gas configuration. Now, I will be assigning a homework on this so you can practice, so stay tuned for that. I'll mention that shortly. What I am going to show you to wrap up today's class is there's 5 what we call anomalies. Anomalies are exceptions. Okay, there's more than 5, but these are the most common 5 exceptions. And what I mean by that is that they are elements that don't follow this pattern. They have a unique electron configuration. So I'm going to show you who these 5 are, and I'm actually going to do all of them on the board. Let me erase this here. And I'm going to tell you who the 5 are and where they are on the periodic table. I'm also going to explain why they're exceptions. There's a reason why they don't follow the pattern. It actually makes a lot of sense when I explain it to you. The 5 elements is, if you look here, this is 3D1, D2, D3, D4. Right over here is chromium and molybdenum. They're in the D4 column. Chromium and molybdenum. And the other exceptions is, if you look here, this is the D9 column. This is where you have copper, silver, and gold. These are the 5 exceptions. Okay? Now, let me explain to you why they're exceptions. Let me give myself a little space here. Okay. Let's start with chromium. Chromium is number 24. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Okay? okay? Now, since we just learned how to do the shortcut, let me put molybdenum down here. Since we just learned how to do the shortcut, we might as well practice. Chromium is in period 4, so it's going to use the noble gas from period 3, which is argon. Argon's number 18. Look at the shortcut for chromium. It'll be argon, okay? And then it's 4s2, 3d4. Now, that is what you expect chromium to be. However, chromium does not follow that electron configuration. I'm going to show you what it does, okay, and explain why. I'm going to do an orbital diagram of the last two only. We don't need this part. 4s has 2, and then 3d has 1, 2, 3, has those boxes, and then look at this. 1, 2, 3, 4. All right, guys, here's the explanation. That's the orbital notation of the last two from the shortcut. I want you to notice something. There's an empty room. This guy over here is sharing, and he sees that there's an empty room. So you know what he does? He says, why am I going to share with you when I can have my own room all the way over there? In fact, this is why it's an exception. This guy actually jumps over here and leaves this room and fills that empty room. And you know why this is more advantageous? Because now everybody has their own room. Instead of him being there sharing a room, he jumps over here to have his own room. So, instead of chromium being like this S jumps over here. So the real configuration for chromium, it's not 4s2, 4d4, it's 4s1, 3d5. This is the actual electron configuration for chromium. Okay? Now, I'll show you molybdenum as well. Okay, molybdenum is right underneath. So, molybdenum, here's the shortcut for molybdenum. It's krypton, and it's 5s2, 4d4. That's the shortcut for molybdenum. You could look it up and do it yourselves. Same thing, guys. What happens is, for the same exact reason, let me make another box here. This guy jumps over here, and instead of it being 5s2, 4d4, since he jumps over here, it's 5s1, 4d5. That's the actual electron configuration of molybdenum. Same reason as chromium. Now, for some reason, tungsten, who's underneath molybdenum, doesn't follow this pattern. Tungsten actually follows the normal pattern as expected, which is odd. So only krypton and molybdenum from that D4 column are exceptions. Now, in the D9 column, where copper is, all three of them do it. Okay? So let me show you copper. Copper is number 29. Let me do the shortcut. If you notice, copper's over here. So the shortcut would be to use argon. So I'm going to put a bracket here for copper. And here's the shortcut. It's argon, then it's 4s2, 3d9. That's 29. That's the shortcut for copper. Now I'm going to show you what happens here. Let's do the configuration, the orbital diagram of the last two. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now you might be wondering, what's the difference here? Why, because there's two here, he goes here, there's two there. What's the difference? What's the big deal if this guy jumps over here? Okay, I'm going to tell you what the big deal is. It'd actually rather be here and pair this one up and leave that one alone, because technically the D room is in the third energy level. So it actually rather pair up here and fill the D room and have the D room complete and leave the 1 electron on the 4s. So I'd actually rather pair up over here so that the D room is completed, so that third floor is done. Even though you're thinking to yourself, what's the difference if there's 2 here versus here? The rationale of this one going over here is to actually complete the D orbital. Okay, it's more stable by doing that. Now, silver is right underneath copper. The shortcut for silver is krypton, okay, which is number 36, and then silver is 5s2 3d9, okay? Now, just like copper, the electron's going to jump over here. The electron's going to jump over here. So the real configuration for copper will be 4s1 3d10. The real configuration for silver is going to be 5s1 3d10. That will be the real configuration because he's going to jump over here. Okay. Finally, let's take gold here. Gold is right underneath silver, so we'll use xenon as the shortcut, and it's 6s2. Okay, and this one is, I made a mistake here. Sorry about that. That's 4. Just caught that. This is 5d9. Okay, so make sure you fix that. So here, same thing happens. He's going to jump over here to complete the d orbital. Again, I'll show you visually. He's going to jump over here to finish that. So it's not going to be 6s2 5d9. It's going to be 6s1 5d10. That's how it's going to be. These are the 5 exceptions, okay? And there's reasons for it. As you can see, energetically, these are more stable, okay? So, so far, here's what I would like you to do. You have 2 methods of how to generate the master sequence. You can either use the periodic table method, which is the one on the board. I also taught you how to use the diagonal method, okay? I don't care which method you choose. You're going to have a periodic table on an assessment with you anyways. And you should be able to do an electron configuration, an orbital diagram. Tell me what block the element belongs to, okay? Using an orbital diagram, you can answer how many unpaired electrons a specific atom has. And there's a shortcut called the noble gas configuration, which is what I used here. Now, in addition to all of that, you know, there's some exceptions in the periodic table. They're called anomalies. And these 5 are the most common anomalies. It's chromium, molybdenum, okay, they're in the D4 column. And then in the D9 column, you have copper, silver, and gold. And they're anomalies because, as you saw, the electron jumps from where it should be over to the next level. Okay, so you get something unexpected, but that in real life, that would be the configuration that you would see for these 5 elements. Okay, I will touch base with you. Our next topic, we're going to review some of the things from quantum numbers. I hope that what I told you today will be able to guide you so that you can do the classworks and homeworks that I will be assigning. Okay, thank you, and till the next one.